Hello, everyone. Good morning, good afternoon, good evening, depending on where you're collecting from. Welcome to this session of the webinar. Actually, this is the first session of our GLOSOLAN Spectroscopy webinar of this year. I'm glad to see all of you again. My name is Yipen from FAO. I coordinate activities related to soil spectroscopy. And it's my privilege to invite our renowned speaker from Canada and Professor Asim Biswas, who is specialized in field spectroscopy. So today's webinar will take us to Canada, and he is one of the earliest scientists in our community who works with field spectroscopy. He's going to talk about today how his experience to apply spectroscopy in the field and to support digital soil mapping related activities. So before I start, I would like to kindly inform you that this webinar in the Zoom setting is set up as the webinar mode. So the participants won't be able to activate your camera and your microphone. But please feel free to write your questions in the QA session, and our guest from the panelist will be happy to answer your question either online or by typing answers. So after the presentation, we will be following some discussion session. So if we see some questions can be interested to bring to the discussion session, and we will leave it to be discussed later on. And in the meantime, please feel free to interact to each other in the chat session. And but please don't raise your question in the chat, because that will be quickly passed out and we might miss your questions. So please post your question in the QA session. So without further ado, I will pass the floor to our distinguished speaker, Professor Asim Biswas, and the floor is yours, please, Asim.
Thank you. Thank you very much, Penny. It's really nice to see and participate in this webinar. I have been attending them in the last year, and now I'm speaking here. So thanks to FAO, thanks to the GLOSOLAN community for inviting me. And I'm hoping to share some of my experience on the field spectroscopy. What do you observe? Again, I don't know. If you ask me, why did I put a title? Can you take vis-NIR spectroscopy to the field? Maybe. I don't know whether I will be able to definitely answer that today. And can we leverage those spectroscopy collected data for the digital soil mapping? Again, maybe. So what I would like to do, take you through some of the research project we have been doing in our lab in Canada and in collaboration with many other countries as well. So before I start, I would like to thank FAO and thank my co-panelist here. So we'll be happy to help from our research group in terms of what is going on, some of the questions. I'll be more than happy to answer those questions as well in online platform. So as Dr. Pengi said, my name is Asim Biswas. I am from University of Guelph in Canada, which is close to Toronto. I'm a professor and graduate program coordinator. I look after the graduate program, but I'm also the research chair in soils and precision agriculture, as well as a current member of the Royal Society of Canada College. The group we work with is my research group, Biswas Soil Lab. You will see some of the logo throughout, and we'll be happy to talk more and explain some of the things what we're doing. So with this, I would like to start, and I would like to go back to some of the slides and graphic that was actually posted many, many times in FAO websites and many, many presentations. You have already seen that. So every time, even when I woke up this morning, I was eating my breakfast. So I am here in Canada this morning. I know many of you probably had your lunch or had your dinner. So every time we eat food, did we ask ourselves where our food come from? And if you see, if somebody is answering, my food come from supermarket shelf or a grocery stores, I don't know, sometimes I try to control myself and not to jump on them. Like, no, your food doesn't come from your supermarket shelf. It comes from soil. 95%, more than 95% of our food come from soil. And not only that, soil is the strategic resource, not only for our food security, but our climate mitigation, infrastructure development and support. We breathe fresh air, we drink fresh water, good quality water. So anything you talk about, it is that soil supports. And that's the reason. So if we think about 7 out of 16 SDGs, Sustainable Development Goals, soil was marked important. Soil was mentioned in any 7 out of 16 SDGs. So you can think about the criticalness. And when you looked at where we are in terms of these, our natural resources, but again, natural and almost like a non-renewable resource, because if you think about an inch of soil can take up to like a couple hundred years to 1,000 years to form. So you don't call them as a renewable resource, I guess. So in that non-renewable resource, and if we keep utilizing that or overusing that, where we will stand? Because the days are coming, the time is coming where we need to grow more food for our extended population from the less land, because a lot of land are taken up by many other development, infrastructure and others, or even the road network. And Worse weather. So this year in Canada, we almost didn't get snow at all. This is surprising, like that from a Canadian winter, we're calling them 3 scattered event of snow. It's just scary. So basically, we have to grow more food in a less quantity of land or less amount of land in a bad weather. So if you want to grow more food and if you want to do that, we must actually work through of the information or work through what we have, and we should manage them very well and very efficiently so that we don't stuck in the problem going forward. So when you looked at like a initiation of the International Decade of Soil, and this is 9th year, so we are almost finishing up that International Decade of Soil 2015, when FAO announced that. In that soil resources, we identified the problem where we are. We have seen the criticalness, we have seen the problematic, we have seen the issues of soil health, carbon depletion, nutrient depletion, anything you talk about. And not only FAO that announced the global report, and followed by many provincial and federal government agencies, they actually announced. For example, this is a report from where I live, Ontario. So Ontario Ministry of Agriculture, Forestry and Rural Affairs, they published their report. It's called the New Horizons, Ontario's Agriculture, Soil Health and Conservation Strategy. So based on the resources, where do you want to go? And true speaking, I'm looking for the 2025. Next year, we're hoping to when this updated status of these resources we have. So we are hoping to see where we are in last 10 years, what we achieved. But true speaking, if you want to achieve that good, if we want to achieve the target we want to reach with our soil to feed that ever increasing population, and with the food grown in a less land and in a bad weather, we really need to manage it well. And if we want to manage our soil well, how do we manage if we don't know it? So that means we need that information, we need that data. How do we get that data? We need to measure it. We need to measure our soil. So if we can't measure something, you can't manage it. So we can only do a better management of our natural resources. We can natural resource, our soil, non-renewable resource we are talking about here, only through the better measurement. But traditionally, what we do, if we go and start measuring our soil, we go grab soil from the field, bring it back to the lab, or even some of the sensors, we put it together, try to come up. But traditional chemical analysis will cost a lot of harsh chemical, cost more money, include more labor, and it will take time to get the data. So what happened in this context over the last several decades, we have seen the progress in alternative way of measuring our soil. That's the sensor-based measurement. And that sensor-based measurement, often proximal soil sensing, that means when we measure soil in a close proximity, within 2-meter distance, more specifically, if you think about that, proximal sensing offer a range of alternative. And when these alternative approaches we're looking at, among the proximal soil sensors, spectroscopy tend to be very promising. And that's why we are having this platform today. And we're talking about this GLOSOLAN Spec. If you think about FAO-GLOSOLAN Spec initiative, that's what we wanted to come. We wanted to see a globalized approach where the spectroscopy and other sensor-based measurements could come in, but GLOSOLAN Specs particularly how we advance our soil spectroscopy research, how we advance the spectroscopy-based soil analysis so that we can make a better decision. Now, what is spectroscopy? I know this platform, if you have already attended many other seminars last year, and all the recordings are available on the FAO website as well. So spectroscopy is a type of proximal soil sensors or proximal soil sensing technique that evaluate electromagnetic radiation against an object. So what we do, we look at the light. So anytime in a visible light range, if you see an apple red, why is that? Because when all the light rays goes onto that apple, except red, everything comes back. So you can see that red. The same way within that visible range, if we shoot that light onto soil, what will happen? And same way, if we look at the near infrared range beyond our visible range, which human eyes cannot actually detect the changes, but some of the sensors could actually detect those changes. Now, can we take that spectroscopy to the soil and the GLOSOLAN spec? I know we're talking about what happened very briefly before I go forward. Traditionally, what happened, you have the light source, complete light spectrum, and you want to actually, just like the background of my my video, you can see that one light source is coming, and with the prism, you can actually deviate the different individual lights. The same way, we can actually, from a complete light, we can differentiate different sources of light or different bands of light. And when that bands of light goes into the soil, it vibrates, it actually reflects, it absorbs, and we can measure them. We can measure that reflection, reflectance, or absorbance in the light. And once we get that absorbance, we try to connect back to a certain property in the soil. How does that work? So basically on your x-axis, when you look at the wavelength of your light, and on the y-axis is an absorbance. Now, as this blue light, blue line or a green line going forward, you can see some of the cases peaks and valleys are there. So those peaks are almost showing that higher absorbance in those places. So that means less of a reflectance going on. Now, each of those absorbance peaks or valleys is actually associated to a fingerprint. That means we can connect them just like a human fingerprint. We have very unique to us. The same way, each of those peaks are unique to a certain property of the soil. Now, what could happen if we take a look when these peaks or valleys happen and connecting back to a particular property, a particular chemical constituent of the soil, then we know how much of that light absorbance is happening and how much is coming back or how much is staying in the soil. So if you think about the intensity of those lights, the intensity of the light coming back, that intensity could associate it to the level of material in the soil present. So this is quite a common, you have seen many, many times, probably a similar graph like this, where x-axis again is the wavelength, y-axis is the reflection, is variation in the soil organic matter in the soil and how different levels of organic matter could actually produce different visible and near infrared spectrum. So there are different equipment that can do that. But again, just I want to clarify, I wanted to show some of the equipment, but I must clarify that I don't work for any of this equipment company. The names and the list I provide here may not be an exhaustive list. List are just taken from their websites and others. So I don't represent any of the company and I don't have any financial interest of any of this. So this is only for the market available and some of the commonly used equipment available in the market. For example, ASD Field Spec 4 or ASD Field Spec 3. So when you look at that, this is very commonly used, and even some of the global spectral library, we have seen a recommended spectrometer to be a field spec spectrometer. Or spectral evolution, many research we have seen with the spectral evolution and how they're measuring it, or even various technologies from cancers. And they also have a spectrometer that could actually go down the depth or even use the same spectrometer in the lab as well. In a recent introduction, I have seen new spectra where they're taking the spectrometer to the field as well and with the cell phone control, or we have all heard about the soil scanner, and that's have done almost revolutionized at the very beginning of how the spectrometer could actually measure some of the soil properties, or even the ocean optics and ocean insight, some of the range of spectrometer that could be utilized as a fundamental component of any soil spectrometer. Not only that, and recently came across one of the spectrometer from Canada as well. You can take the spectrometer out in the field with a one click of a button. You can get some of the measurement as well, the GLOSOLAN, or even much smaller within on top of your palm. You can take that, and it's quite a range as well, 900 to 1700 nanometer in IR brand. You can see the spectral reflectance for the soil as well. And not only that point scale measurement, you can put the spectrometer behind a tractor or behind a wheel and drag it along the field to get continuous measurement on your spectra, or even you can go down with the depth. So this is an equipment from iScan and VSP 4000. And there's a new one coming up as a 3500 from various technologies as well, where you can go down the depth and get the spectrometer measurement. One of the recent one we came across as well is soil reader. I have seen that one, and what happened, the disk goes around in the soil and continuously get the measurement, and it could be fitted to any of the equipment or any of the operational equipment, farm equipment we can see, so that we can continuously get the spectroscopic data in the field as well. So this looks like just a disk, and that disk will have a window and it goes through. So basically, again, we want to get the large amount of data on the spectroscopic measurement. Now, if we see how these machines have been performing, how this equipment has been performing, and how the research over the last several decades, it shows really amazing promise on spectroscopy. It can measure multiple soil properties simultaneously. With a one scan, we can get several properties that are directly associated with the spectral range we're looking at. And some of the cases, we don't have even a direct relationship. We try to develop the secondary relationship or a tertiary relationship to get those measurements or get those relationships built. It has made the soil analysis cheaper, simpler, so you don't have to go through chemical soil processing analysis and all those things. You require less labor, often much environmentally safe because you are not using chemical and disposing them. It is quite portable. Almost all the equipments are. You can take it to the field or lab to lab shifting and other things is possible, as well as scalability of these processes. So spectroscopy shows a huge amount of potential, and this is where the GLOSOLAN spec came into action and creating that global community where we can talk about the spectroscopy. So when we are using this equipment to measure soil properties, we can do both in the lab and the field measurements as well. So what we have seen so far, lab measurements in an idealized situation, control condition on a benchtop condition. What you can see, you bring a soil sample, dry it, ground it, sieve it, and create a very ideal soil sample. And when you measure them with a spectrometer or any of the spectrometer in the lab, you tend to find a highly promising result because it's almost very much highly correlated soil variable we can see. So these are ex-situ ground and process sample, sieve sample, and in this control condition. So this provides a lot of opportunity. But what will happen? Still, we need to go out to the field. We need to collect sample, process them. It requires the labor, it requires time and all. Only thing we are actually replacing here or leveraging here is, can we replace that chemically associated measurements to more of a sensor-based measurement in this aspect. So what happened? We try to take them to the field. We want to see how can we actually explore this equipment in the field condition as well. So in this field condition, it can help you develop that on-site measurement and decision making. Many times you don't have to wait that bring back the sample and dry them, process them, scan them, and get the measurement. But can we make a decision rather than just sending and waiting for a couple of days to get the data? With a measurement, can we make a decision right there? So to reduce our transportation, preparation, and all those things. But one of the issue we found that just like a light, when you take a photograph or when you see something in the dark versus something in the light, it looks different. I could be looking at a completely different object. The same way, when we are looking at the soil in a lab condition versus field condition, in a field condition, you can have a lot of environmental impact on the physical condition. Environmental impact means how much of a soil moisture is there, how dry or how wet is there, how much of a light condition. But again, you can control the light condition, but the physical condition of the soil as well, how surface roughness, you can think about how compacted the soil material is. So many different physical and environmental conditions can impact your field measurement. Moreover, the variability of the soil, some of the instrument performance when you are actually using it in the field, the battery, the light, and everything could actually impact that. So there are some challenges in the field spectroscopy, and true speaking, that's why we haven't had a lot of reports coming up in there. But again, that's why at the beginning I'm saying I don't know whether I'll be able to answer that question, but I wanted to put that question to in today's lecture, that can we take this vis-NIR spectroscopy to the field? And if we do, if we can take them to the field, the data generated from that, can we leverage that for further process? Further process, one of the things I wanted to mention here is the digital soil mapping, because if you really want to make that decision, often the spatially distributed data you require. Spatially distributed data means I really think about if you want to make a better decision, you want to know where things are and how much things are. So that means where those soils are and how much of those properties at different locations are there. And digital soil mapping has shown promise over the last 22 years now, with the first paper 2003 with the digital soil mapping term coined, but the concept has been there in the community for quite as long as well, that predictive soil mapping is really creating the spatial distribution of maps. So I wanted to say, can you take that vis-NIR spectroscopy to the field? And if we do generate the data using the spectrometer or spectroscopic technique, can we utilize in digital soil mapping? So rather than going a structured way, I just wanted to take you through a few snapshots of studies we have done, some of the case studies. The way it's structured there, of course, the lab measurement and the process samples we are working on, I want to show how it is. And we have seen reports, we have seen positive reports and very, very promising data in that case. One of the example I would like to bring that we are developing a soil spectral library, local spectral library as well. We scan, I think about 15,000 samples now. And those are processed ground soil sample, working with the local ministry. We're working on those samples. Now, what I want to take it to the next step, if we're working on a lab in a process sample, dry ground and sieve, but can we remove the dry ground or sieve condition if we grab a soil sample from the field condition and measure them in the lab? So the soil sample is an unprocessed sample, still have a moisture and other environmental impacts in there as well. How that will perform? Even the measurements done in the lab condition, so that we can avoid the uncertainty of the instrumentation and other things in the field condition, but still we're keeping that sample collection and so. And what is the success rate? I want to show that through our case studies. And finally, I want to show if I don't even collect those soil samples, I take the spectrometer right in the field and try to measure this. So in situ unprocessed samples, what those could happen. So this is the 3 case study I want to show. And once this could be established, I want to see if this data set I can leverage in digital soil mapping so that we can make a decision. This is the 4 quick case study I will show today. So the first one is that so what we wanted to see it here in that sequence, we want to see a dry process ground sample, or you can see more of an intact soil sample coming out of the field, or take a spectrometer out in the field, measure in situ. Once we get that, can we leverage with other information available to develop digital soil map? So the first one, can we predict soil properties from the process sample using vis-NIR spectroscopy? So this is the first case study, as I mentioned. In that case study, what it did, I'm from Ontario in Canada, and in Ontario, we have ran through some of the soil survey program by the Ministry of Agriculture and Forestry, or Ontario Ministry of Agriculture, Forestry and Rural Affairs. It's called OMAFRA, and they have collected lot of soil sample. You can think about 1,505 soil sample from one of the province and another 1,150, 1,165 samples. So these are the profile samples. So each of the profile sample have multiple soil horizons. And then some of the other projects we are running ourselves as well. For example, here we included as a wood drill project. one of the local service provider we work with company. They collect soil sample as well. So in this project, about 10,000 plus soil sample were scanned, but not all the soil samples are utilized, because when you look at descriptive statistics of the data, I know it's a busy table, just want to focus that many of the soil property we looked at quite a broader range, like a pH from 3.3 to 9, organic matter 0 to 85%. Canada has a lot of organic matter soil, organic soil or peat soil. We're looking at same with some of the available nutrients and others. And you can see the last column where we're talking about soil sample between 8,700 to 9,500 almost. So within that range, so we have a large amount of sample to work with. We utilize vis-NIR field spec 4 to actually measure those properties. That's the way we did. We take the soil sample on a petri dish, and you can see some of this organic soil. These are highly peat soil, and it's coming from natural environment like peat and bog area, as well as sandy, clay. You can see the diversity of soil condition. Using contact probe of ASD field spec 4, we measured at least of 3 scans for each of the soil sample from that petri dish with a contact probe, so that we get those measurements done. Once we get those measurements done, we run through some of the pre-processing technique, like a cleaning up of the spectra, like edging, trimming the edges, so that we don't get that edge impact or convert it into reflectance or absorbance, those conversion as well. Once we clean up the spectra, we did some of the pre-processing. And as we go through, as we're developing this library, we wanted to see a range of pre-processing techniques and see what pre-processing technique tend to be better for this library as well. And once we pre-process the spectra, we take the data through different modeling techniques. And in that modeling techniques, of course, the splitting approach we have taken, we have large amount of sample. We are able to actually put a certain amount of certain number of samples as an external validation, and the rest amount we work through calibration and cross-validation approach to establish the model. Once we do the model, of course, the uncertainty associated with the prediction is another approach as well. We always carry it forward. A range of pre-processing algorithm. I know it's a busy guy. I don't want to go through all of them, but from first derivative combination. So again, we looked at some of the papers to see what is the best pre-processing algorithms, and pre-processing algorithm combined with a different modeling algorithm, very traditional, the one we use, the PLSR approach or partial least square regression, with more of a data-driven approach like random forest, Q-based, GLM, or even going into more deep learning techniques as well. So we really wanted to see what is that combination of technique could actually help. One quick example, I don't want to take you through, maybe a little less, it's a lot of numbers on the slide. But what I've done, each of the cases with each of the modeling technique, we estimated range of performance indices like R-square, concordance value, MSCR, MSC bias, a range. Like we did not stick it to, because we want to see many places we report to one or other performance index. And we looked at that calibration validation and validation external. Cal particular model is a calibration set, val particular model is a validation set for that model, and val particular set is that external validation model. When we looked at particular for soil organic matter, we see concordance is quite in agreement. You can think about like CCC or concordance value almost every time is more than 0.9 and above. For each of this model, we're looking at the 10,000 soil sample here. It's not only organic carbon, we looked at all other properties like calcium. We saw very close agreement between our 1:1 line and the regression line as well. The blue color are our calibration data. The orange color is our validation data. Then we ran through that model using the external validation as well, and we reported the data for both. So again, clay, sand, or other soil textural properties as well, we have seen that promising result as well. And this is not surprising, or this is not unusual, because we have been seeing in the community the positive approach of that processed dry ground samples. And we are very proud about it, because we are able to figure out how to measure, how to use that field lab spectroscopy to get that data. And what we extended in this case as well, I just want to highlight here that many cases when you are measuring multiple property, but if you want to talk about the soil health and soil quality, it is not enough using a one particular property. So we took an approach, an index-based approach to calculate soil quality index, where we actually create a weighted variation or weighted approach for different properties we measured in the study to create a soil quality index. Now, we did not stop there. For that soil quality index, what we did, we measured the SQI, soil quality index, which is nothing but based on the calculation of the measured or lab measured properties. And then we can also calculate our SQI based on the predicted properties, individual predicted properties. And then when we also predict direct prediction of SQI. So this is the three different approach. We take the lab data, calculate SQI. Now we predict the SQI itself, or we calculate SQI from the predicted data and calculate SQI from the measured data. This is the three approach, and some of the variation you can see. This is again is a more normalized approach between 0 and 1. We try to come up so that everybody can get in the similar weights. And when you look at the calibration for the soil quality index, not only multiple modeling approach like PLSR, QBIST, and RF, we look at, or random forest, we looked at for calibration, cause validation, and external validation for about that. I think this one done about 8,900 samples as well. So we have seen that promise, not only talking about that individual property, but we can take that combination of property to go forward and talk about our soil. Now, the next I wanted to show in the storyline of that 4 different case study, I'm sorry, can we predict soil property from unprocessed sample using vis-NIR spectroscopy? So unprocessed means we still collect soil sample from the field and bring it back to the lab and then do the spectrometer. So we are not taking the spectrometer to the field, but we are processing the sample in the condition where we see in field. So in this case, what we have done, we ran a study about 205 soil cores we collected from 13 farms across Southern Ontario, very close by around Guelph, where I live and work as well. So each of these farm, when we went down there, multiple soil cores are collected based on some of the approach. And this is a collaborative study with Woodrill. These are the farms under Woodrill, the service provider we're talking about, an agronomist company, crop service company, crop supplier. So basically they work with the farmer and manage their farm. And we went down there, we collected soil core, and that profile we described following the Canadian soil classification system. We divided into multiple horizons based on their properties, and then we sampled those soil based on the soil. Sorry, we sampled for each of the horizon. So now the sample split by the horizon, we had about 1,046 sample total. So in this study, what we wanted to see, if we collect the soil sample and take it back, how the spectroscopy could work. So initially what we did the similar way like the other study, we take that 1,000 sample, bring it back to the lab, about half and half we segmented, half we air dried and ground so that we processed their samples, and half we left in the field condition with the airtight container or Ziploc bag so that we don't lose moisture and other things as well. We measured pH, EC, organic matter on all samples, and a subset of sample we measured soil texture as well, using a combined approach of sieving and hydrometer method, so that we go for sieving for the sand particles, and then we went to do hydrometer method. And then we collected 2 sets of spectra, one on the air-dried, sieved and ground processed soil samples, while is the other spectra is an unprocessed field moist samples. So what we did on the soil course, we have about 1,046 samples. We collected 1,046 dry spectra and field spectra. We divided both case, we divided that 70-30 split using calibration and validation. Dry spectra, then we go for a pre-processing and modeling technique in traditional way. But field spectra, what is required because of an environmental impact, we want to transform that spectra and identify or basically almost like a subtracting the impact of those environmental impact. So we call it as a transformation. So when you do the transformation, that transform data set, then again, we split into 70-30 and we go for the modeling, pre-processing and modeling as well. So what we did, like just completely based on a dry spectra, we have seen a very high prediction for first derivative and gap and second derivative gap tend to be producing very good predictability for our case, and majority of the soil property, random forest or cubes tend to showing quite a good prediction as well. Again, it's a very busy graph. I just want to take this masses from this table is that two different or three different pre-processing technique tend to be coming up on the top, and among the modeling cubist random forest tend to be showing quite a bit. In some cases, some property we have seen also PLS are performing good as well. So best predicted organic matter, percent sand silt, worst predicted AC and clay, processing first derivative gap and RF. But again, this is that dry process samples. Now, what we did that unprocessed soil samples, we took the 3D application of spectral data on the field soil sample, true transformation matrix. We used the one I showed in that graph, the transformation. One, you call it as an external parameter orthogonalization or EPO, and another is a direct standardization. So once we get that done, we have the dry spectra and field spectra. We created 70-30 split for both case. And that 70% of dry spectra, we try to develop a transformational algorithm with a field spectra. So how much of a difference is there? Though it's the same soil, mainly due to the environmental impact, you see the spectral difference. So we wanted to create the transformation matrix. We want to see the difference, and based on the difference, we want to create a transformation algorithm that could help us transform the spectra. We call it as a transformation matrix. And once we get the transformation matrix, we take that field spectra 30% and we try to predict that property as well. So once we have the transformation matrix, get the transformed data, they want to go for the modeling, and where this 30% dry spectra, we can take that one to validate as well. So both transformation method determine the difference between the dry and field spectra. Of course, we know it's supposed to be because it's an environmental condition. So in summary, that EPO gives us a specific location difference identified, or DS average across the data set as well. Again, two fundamentally different transformation algorithm, and that is why we wanted to check it as well. So once we look at that, once we look at that, we look at the dry spectra. Once we look at the dry spectra on the second column, first column is the name of the models. Second column is a dry spectra. We just use an adjusted R-squared to showcase here. And field spectra, third column is a field spectra before transformation, and after transformation, we can see those differences as well. And when you do the transformation using a DS, and we have seen the improvement in terms of the predictability. And this happened between your second derivative and gap, this particularly to particular pre-processing algorithm and a combination of modeling that tend to be showing the best approaches out there. So it did show, like when you use that particular DS approach using our DS algorithm we used to confirm or modify or transform our field spectra, it did improve the predictability. So that means we really need to add that additional processing technique. If we are really talking about that field-based spectroscopic measurement, we can actually get those done. Now, we have that data set, but we still have to bring it back to the lab. Now, in the third section, I really want to say, can you predict soil properties in situ using vis-NIR spectroscopy? Like, again, in situ, which is kind of a third part of this presentation we're talking about. So what I did, for example, we collect the soil core like that using a truck like it, and we collect the soil spectra on the right side. Thus, I'm collecting soil spectra. As we go down, we collect every centimeter or every few centimeters the soil spectra. And if we plot that soil spectra as we go down, we can see the differences as well. So what we did, we collected 3 application spectral data, collected each situ. So that means location 1, 2, 3, and each of the location we go down to up to a meter depth and we collect soil spectra. Once we collect that, Then we use the same two transformation matrix like transformation algorithm, DSNR, EPO. Now we have two different set of matrices for two different data. One, you have a field moist sample, which is an unprocessed sample spectra, and you have an in situ spectra. So we can define dry spectra, field spectra, and in situ spectra. So if we three different, we'll try to talk about that. So previously optimized processing and modeling algorithm we utilized. How we did the transformation here. So in situ, dry, and field spectra, we separated 70-30 split, and that 70-30, just the way we have already talked about dry spectra and field spectra, we use the transformation algorithm, we create transformation matrix, and based on the transformation matrix, we transform our data and then go for the modeling. Now, so when you're looking at in situ spectra, in this case, it's a very similar way. So rather than the field transformation matrix, now we are looking at the in situ transformation matrix. And we are looking using the 30% data, we're looking at in situ transform data. Now I have two sets of data. You have a dry set, that is dry spectra, then you have a field spectra, then you have an in situ spectra. And we take that 30% to validate. And if we look at some of the numbers as well, so we did not get to all 205 soil cores, but we're going to 150 or something, 150 plus soil core. We went about 621 in situ samples we got. We did the transformation and the modeling algorithm, very similar way we have done for the field spectra. So 153 soil cores we got, or 621 samples. We split them 70-30 and go through transformation and get that number. So again, we ran both as a sample and as a profile as well. So when you're validating, we wanted to make sure, see the both approach and see their difference. If we keep one sample out cross validation or keep one profile out cross validation, because the connection between the soil horizons, so we can often take one soil horizon as a one sample. So this is where you can see those numbers. The first number is nothing but the sample number, physical sample, and second number 153 is nothing but your soil profile samples we have. And when you look at, again, it's a very busy table. So the dry spectra, before transformation, we're looking at dry, field, and in situ spectra, that first three column, and how that prediction looking at. So if we take a look, the predictability for like a particular pre-processing technique, first derivative and gap, we see the highest prediction. Then as we go through there in the in situ, we tend to find less and less predictability. But what we did, then we take the DS field matrix and DS in situ matrix, and we have seen a major development in terms of that predictability. And in all cases, PLS tend to be showing the best prediction as well. So compared to our EPO matrix, DS showed the best performance, and DS showed that performance both in case our field matrix and in situ matrix. So we did not see a lot of improvement in this case as well. So that means whether if we go from a field to in situ, can it add that value or not? So we have been asking that question as well. And I think we'll talk about a little bit more. So in situ spectral prediction, we have seen again, busy graph, the two first derivative gap, DS field matrix on the top table, and the bottom table is DS in situ matrix, which is three different pre-processing technique and 4 different modeling as well. And you can see quite a high amount of prediction, but we're scared that prediction may be impacted by the number of samples we had. In this study, we had only 205 soil cores, particularly in situ spectra, we have 153 soil cores. So all soil properties are predicted well by DS transform in situ spectral data, in situ and field spectral data as well, which in the second part we have seen. And it may suggest model overfitting because the value we got. Now, so far we have seen that, yes, we can take the spectroscopy out in the field and modify the data and modify our algorithm and processing and get the data. So if we go there, now this is the question we're asking. Okay, if we can take the field spectroscopy or spectrometer to the field to collect data, can we integrate that into digital soil mapping? That's the fourth segment we are talking about. So I will just quickly show a case study where we have done. This one is from Montreal Quebec. We started about this field work quite a long time ago. So quite a variable 26 acres plot. It's not very big plot we're looking at, but highly variable soil type from a coarse sand to a muck soil. You can see this is the soil type. So what I did, we kind of created a gridded approach, and we collected soil core from about 32 locations. Now that 32 location, so what we did on top of that 32 location, we take our spectrometer and actually dig it through the soil, and we collected another 148 soil samples almost, soil spectroscopy, in situ soil spectral data. So what I did, we collected soil core, and using that core like that, and then we take the same spectrometer in the same field, and each of those location of 32 plus additional location, we collected soil spectra we get. So what happened, we got that profile spectra, 32 soil properties location, but 148 spectral data. So out of 148, we separated 32 and 116, which we don't have the soil data or lab data, but 32 location, we have spectral and soil data. So what we did, we use a spectral partial least square regression or PLSR, which is quite common for various regions I have been talking about. We have seen the performance for a field level data, PLSR, we want to continue there. So it reduces the high collinearity of the predictors, it fewer factors to explain most of the variation in both predictors and responses as well, and Liborn cross-validation is easy as well. So what we did, we created that model using the 32 soil core, and once that model is established, we predicted that 116 location as well. So at the end, we got 148 predicted location. Though we are measuring soil property at 32 location, we want to take it and get that. So really intensifying that data collection using the field spectroscopy to 148 location. Once we have that 148 location, we wanted to go and develop the maps. But one question to ask here, if we go out with a field spectrometer, where should we sample? So in this study, what we did, that we have 148 location, but we kind of imposed one over another different kind of a sampling technique. We wanted to see how different sampling technique could actually include there or predict soil properties better in help the mapping. So we use grid sample, grid random sample, transect sampling, random sampling, and stratified random sampling. We created that individual, and that's why it came up to that 148 location. Once we have each of the sample design, so we created using that 5645, 3744, or 42, we created the map. So we have that 148 location, every 10 centimeter soil property predicted from the spectral data, and using the sample design, we want to develop the map. So this is a quick overview how the sample design look like. So you have all the sample data together, and when you put all the sample data together, what we thought, this is kind of my best of best I can get, because all 148 location, and I can get the most information out there. So as we go through here, so individual sampling technique like grid sampling, grid random, stratified random sampling, simple random sampling, stratified random, transect, and conditional latent hypercube as well. So we compare different techniques. And when you compare, of course, the prediction for different soil property as we go down for 3 different models, generalized linear model, random forest, regression tree, we try to see how that RMSE changes with depth as well. Because we are trying to see that prediction with the depth. Now, once we have the prediction, how the mapping could be done. And as we go through the mapping, original data, which we're talking about, a map with 148 location, what we can think about, that's the most intensive data we have and the best variation we can capture through the mapping. And then we develop map for each of those individual sampling technique. When we did that individual sampling technique, of course, based on the sample technique, we see the variation. Now, when you combine that variation, like a carbon stock measurement for the first top 1 meter soil profile, we tend to find that grid random and stratified random sampling, it kind of gave quite a biased overestimated data as well. While grid sample, transect sample, or a random sample, tend to show quite well representation in the carbon stuff that our original map is producing. Then as we go through, we can see the uncertainty associated with those maps as well. So uncertainty, so that means how your original data was there, the map created by your all 148 location and the maps created by a lesser number of samples, the difference we talk about the uncertainty here. And that uncertainty we tend to find across the field, your RMSE values, were lowest for grid sample, transient sampling, and SRS, where the RS and GRS tend to have quite a bit of uncertainty. Now, this is why looking at 1 meter as a whole, but as we have that layer by layer data, every 10 centimeter, we created a map. Every 10 centimeter, we create a map of the original and then 6 different sample design as well. So we look at 0 to 10. Here I'm showing 40 to 50 centimeter or 90 to 100 centimeter as well. But we have done 0 to 10, 10 to 20, 20, 30, 30, 40, all the way to 100 centimeters. And not only that, we are able to actually calculate for each of those measurements, we can see the variation. And you can clearly see here this high uncertainty at the very depth with grid random or stratified random sample. Anything with a random sample associated, we tend to have quite a bit of uncertainty. The main reason we had a very small amount of sample representation, and as we go through the random sample, we did not have much of a representation there. And this is why the road was going and quite a bit of that road impact if we see some of the physical meaning to it as well. As well as the transect sample, you can see the low amount of variation of the points and other amount. You clearly see those variation as well. So what it could help us, that spectrometer can actually help us intensify the data collection. Once we intensify that data collection, we can put them into generate that 3-dimensional digital soil maps and help us to calculate the uncertainty as well, which could help us to do any of the management activity we want to run. So this is the last slide. Just want to check like, okay, I put a couple of the question at the beginning. Can we use spectroscopy for soil? And I would say yes, as good as we have seen globally and many, many research. In this platform, we have heard from many globally recognized scientists and their research. And our research is showing a very similar progress as well. So yes, it is as good as we can do. Can we take spectroscopy to the field? I would say yes, but there are some of the cautions associated with and with the asterisk marks on the top. Yes, we can collect some additional information like soil water data or some of the soil structure, soil texture and other things that could actually help us mitigate those uncertainty during the prediction. And of course, it requires that additional data processing techniques that could actually, so we still need to do work and creating more information about how much of that uncertainty is coming along. Should you do it in the field moisture in situ? So that means, should I do it on the field or collect sample back to the laboratory? I would say that we did not find quite a bit of significant difference between the prediction when we actually collect moist sample and measure it in the lab or measure it in the field. But the issue is that if you want to measure it in the field and with the depth, we need that specialized equipment. But of course, it can save you time, take the samples and bring it back to the lab. So you don't have to make a trip to collect soil sample and scan it in the lab. So reduce the labor, time and effort. But of course, you need that specialized equipment to go down with the depth as well. The last one, can we leverage this spectroscopic technique, data collection for the digital soil mapping? I would say yes. It does show promise. We can actually intensify the data collection, intensify the number of data. But of course, as we go through the depth, more and more number of samples, more specialized equipment. So there is a call for generating that field portable or field suitable spectrometer that could actually help us collect the data as well. So with this, I would like to acknowledge all the funding bodies and many research funding organizations over the last decade, more than a decade, is helping me to generate data. And of course, at different time frame of my last 10 years, you can see it's not the effort of me. And most of the time, I am nobody. I'm just here to present. because the work is done by all these faces and beautiful faces you can see from different times. My student, with this, I would like to thank you and would be happy to answer any question. And of course, my email address, Twitter holder or X account is there. My website is there as well. And the FAO website have my contact information as well. Thank you.
Thank you very much. Thank you, Asmi. And thanks for the great talk. And we have been knowing each other for many years, but it's been a long time. I haven't heard about your work since many years. And also, I think it's also because of the COVID, we didn't really have that much many opportunity to meet each other before we met each other and with conference and everything. So it's good we have this platform and to share the experience and knowledges. And I was watching the participants during the entire of the presentation and always around 200 participants. So it means it's quite interesting your talk.
Perfect. I really appreciate that all. I know is many places, all the participants coming. I should thank you for joining in probably in your bedtime or a dinner time or your lunchtime. So thank you. It's very difficult, I know, when you're talking about globally. And of course, Pengi, I know you mentioned like this platform, and I'm really happy and we really want to see that GLOSOLAN Spec actually connecting us more well actually than what we should do in different platforms. And
Sure. Uh, while you were busy with talking, and we were also busy and behind answering the questions because there's a lot of questions coming, and it's sometimes can be very stressful. I think thanks to your assistant, all of them. I'd like to ask you to turn on your camera so the audience also can see you, and you were working behind of the scene very hard, and we also in the same time we also kept some interesting questions in the end for the discussion. So we will be happy to listen your opinion in a further elaborate some of your opinion.
absolutely.
And I think the first question I can start with it because this question is because the problem of the applying soil spectroscopy in our lab, our lab is the participants he's talking about his lab, is the training limitations such as the software statistical application to calibrate and produce the spectroscopy data for soil. So he or she would appreciate if such type of training opportunity can be arranged. So before asking you to speak, and I can just quickly elaborate a little bit more, is because the reason we initiated this GLOSOLAN spectroscopy initiative because we saw the potential and we also saw the needs globally. Many of the laboratories they really would like to develop the spectroscopy lab. So we started this initiative, and this the main objective of this initiative is to train to strengthen the country capacity to do the capacity development in a different level, country level, regional level. And that's why we started the first activity is to start this webinar program to invite these experienced scientists to introduce their experience. And we also try to organize some workshop in different regions. For example, last week we just organized the Latin American regional workshop in Spanish and focus on both wet chemistry and dry chemistry. So we had a 1 day dedicated for the spectroscopy training as well. Of course, I know spectroscopy is not something 1 day or 1 week training you can masterize. So this is also something, if any of you would like to have additional training, please feel free to reach me. And then our responsibility, our mandate is trying to build a bridge between the scientific institute and the labs, the users, and we will try to find a suitable partners and the institute, the research groups to help you to build your capacity. So that is our mandate. That is also the reason we are trying. Recently, we are trying to write a small scientific paper. One of the sections is to mention that we need a dedicated education program specifically to train a group of the young scientists for the soil spectroscopy. So, Asmin, please feel free to also express your opinion.
No, this is absolutely like I know GLOSOLAN Spec, this is one of the indication. And as you mentioned in that paper, of course, the need for education, need for training, and need for training new generation, I guess that's definitely critical one. And I appreciate this question because we have been saying not only any new technology, any new aspect we're talking about, we should be thinking about just not to showcase the technology and work through that, but of course, going forward, how we can spread that opportunity so that multiple people could use it as well. So in terms of the resources beside that FAO and GLOSOLAN approaches as well, and we often do work like we are creating some of those. Like last year, we offered a workshop where we did talk about processing data and some of the open source coding and all, so that participants could do that. But that was not, I guess, open enough. This is part of a Canadian Society of Soil Science annual meeting. But we have been thinking about creating some of the tools, some of the techniques or videos that could be actually utilized, whether we can host it as an in-person, but of course, COVID taught us a lot of things. So we can do some online presentation, online training as well, particularly the data processing. But it is difficult when you use the equipment, you use it, you learn by doing it, that's easy. But some of the data processing and other things, which I have shown a lot of work on the data processing side, once you collect the data using a spectrometer, how you process, how you extract information. I think this could be possible through other approaches like online training, some collaboration, and providing information resources on top of what GLOSOLAN's activity is doing. I appreciate that question, and I would be happy to take that one further as well as we develop some tools and techniques that could be easily shareable among the community members. I would love to do that. Yeah.
Thank you. And just a little bit complimentary, probably, Asmin, from IUSS level, probably we can also discuss in this regard and to work together. Because what I heard, mostly I heard from different country and the lab is they want to develop spectroscopy and they need a training and capacity development, but they don't know ask who. Actually, I mean, we work in this community. It's a small community. We know everyone. We think it's easy, but actually, for the vast majority of the laboratories, actually, they don't know who is really specialized. They don't know who can be trusted. So I think, I mean, from the FAO level, we also should work more, try to disseminate the information of all the expert, the specialized institute, and to let them know and help them to find partners.
I think I will add to that, like as you mentioned, like I'm also chairing the working group on proximal soil sensing of IUSS, International Union of Soil, and this is an opportunity we have been talking about, Mengi, like how do we actually create that IUSS and FAO partnership where IUSS can bring the capability of the researcher across the world and FAO, which is connection and reaching out, the public outreach could be really, really important moving forward.
Yeah, we have a lot of work to do.
Yes,
Yeah.
indeed.
So the second question is a little bit technical, and it's actually a common question. It's a question you probably need to write a book to comprehensively to give an answer. So it will be a little bit challenging for you to answer in a few sentences. So what is the variability of the spectral measurement based on the soil moisture for the soil sample? What is the variability to basically affect the measurement? The moisture sample.
Yes. So what I would do, of course, like in a natural condition, is an infinite opportunity or infinite possibility those variabilities could come in. because every square inch of soil, if you see, those are variable from the next square inch of soil. But in reality, in the scientific community, we cannot absorb every possible approaches. But what we do, we want to take that more systematic approach and get the data from a certain range. So that the way we are working in our lab condition as well. So we see the opportunity of the impact of soil moisture is quite wide, but we cannot capture all. Rather, we want to strategically choose and go through series of soil moisture content to represent the variability and created a model to try to identify like the research. And that's what we want to make sure that we can get as close as possible to the natural condition, so that we want to represent the natural condition using our research experiments. But in that research experiment, it's not possible to capture all possible dimensions. So what we try to do, we hypothesize in a certain amount that all those things, keeping it fixed, if we move this around with the range, and exactly that way, whether to the variability of the soil texture, we take from a coarse sand to a very heavy clay soil and different soil properties, different organic matter content, and then we vary soil moisture content, and then we look at the soil spectral differences as well. And then we can do the compaction, how compacted the soils are. So we want to take that multidimensional variability and create this model in the representation. So it's absolutely not possible to create that absolute variability into account, but it is possible through the scientific approach, more scientific way, if we design an experiment to capture the range of soil moisture or range of soil texture or range of soil organic matter and see how that reflectances vary. And if we can model that, then we should be able to say how those variations are coming, capturing the variability well enough to represent wide range of soil, wide range of moisture content, or wide range of soil property variation.
Thanks for a very, very short but comprehensive answer. I think this is a tricky part of the soil spectroscopy, because the soil spectroscopy, especially when you go to the field condition, it's really required the multidiscipline of the knowledges. And then it's difficult to give a very certain answer, because you have to based on the different conditions. So,
and the variability of soil is not the new thing. We learned from 1800. And as since my PhD last 20 years, I have been trying to that question, how do you quantify that variability of soil?
yeah. So this is something that this is also back to the same question, is that we need a proper education program, and that's the reason we cannot train someone just 1 or 2 weeks and you will be able to understand this technique. That's why, yeah, great. Uh, and actually, since just now the question is talking about the moisture effect, so I can maybe jump to the another question is because one colleague, one audience asked if you can further explain a little bit about the DS algorithm. I know this algorithm is about removing some effects. So just this.
Yeah, so DS algorithm, particularly when you're looking at, is kind of the overall spectral range, how those differences are coming. The simplest way, yes, there are some of the mathematical process, and these things are implemented in R. Previously, one of my postdoc was there, Dr. G, and her colleagues as well implemented and I think initiated even from Bodhi's work earlier as well, some of those algorithms. Again, this is a little bit of mathematically challenging, and often when you're working on that, we are not mathematician. What we can do, we can implement those mathematical algorithms through some programming and others. So in this particular way, if you want to explain how fundamentally DS is working, DS is really looking at the difference as a whole spectrum, the whole spectrum within the range or wavelength range you have collected. It looks at the variation, and that variation, the EPO, when you're looking at like almost like a segment by segment, is looking at how those variations are coming and try to predict those variations, how much of a change could come in here and how much that change could contribute to the modeling as well. That means we want to create the transformation matrix, how we can tune that field spectra using that modified approach and try to come as close as to the dry spectra as well. Now, in EPO, we are looking at the segment by segment, or while as the DS, we are looking at the whole spectra at a time. Now, in that differences, we want to identify that difference. Now, if we can identify the difference, it's the same soil sample, whether it's scan it in the field, in the moist condition, or in the dry condition. So what is supposed to happen, if we don't have those impacts of your soil moisture, because we have the same texture, same soil property, same compactness level and all, only difference is the moisture content or some of the other environmental factor if we think about. So the spectral variation is coming due to the variation on that moisture content or that environmental impact. So if we can see the changes, we can really tune in that spectra to fix it side by side. Now we are really creating that apples to apple comparison, but how that orange will look like an apple, we are reshaping that so that we can bring it together and develop the model. So that's exactly, so again, the modeling approach, what we're talking, it remains the same. But before modeling, we want to tune that field collected spectra or in situ collected spectra to come as close to my dry spectral condition as well. And that approach, the transformation matrix we talked about, before the transform data, we want to see the transformation matrix, how much of a change happened over a multiple soil property. Then we kind of created a trend. Okay, looks like these changes are associated with these changes. So that means this is what we are looking at within a moisture content. And then we come back with a transformation approach. It's almost like a scaling factor, or many other approaches you use a multiplication factor or scaling factor. In different science, different area of research, we talk about different things, but we want to create that transformation matrix. That transformation matrix help us that field collector spectra to convert or tune in to the closest to the dry.
Okay, thanks. I think there are quite a few different algorithms to apply for the, I think
Yes.
the best way is to try to apply this algorithm on your own data, and you will get
Absolutely.
the feeling.
Yeah, and there are some of the coding, and I think with spectroscopy community movement and a lot of contribution from different researchers from our community in terms of program codes and other things, I think those are very helpful as well. That could actually provide up some resources to work through. And these are open source programs and codes, so you don't have to pay for it. But again, it takes a little bit of time to learn. And as Pengi mentioned, like if you can work through your own data, then you really learn the differences.
Yeah. And another interesting question is talking about the using spectroscopy for detecting the nutrients, because especially this is a field application is directly linked to the crop management, the yield, everything. I think this is farmers are really concerned about. And even another audience asked more or less the same question is, so far we have a lot of research work has been done for the organic matter, for the texture, but not much for the nutrients, and how far away we can really bring this application for detecting the nutrients and related to the crop management, the fertilizer recommendation application, etc. So please.
I would say, like, again, some of the cases I'm very optimistic, but some of the cases I have to be control myself to not to jump around. The main reason is that when you look at the spectral band, if we just take a step back and think about the fundamental principles of the spectroscopy, we are looking at a wave band, and that wave band or wavelength can only carry certain energy. And that energy, when it's actually shooting that light into the soil, so it's almost like a playing that billiard or playing that ball, the same energy ball, if you hit with same energy, then this ball stops and this ball moves. So the transformation of that, like a physics law. The same way, like again, not suitable here, but the way I just want to say it here. So the energy coming in, you know what is the level of energy you are shooting into soil. And that level of energy, how much the reflection could come in with a similar level of energy source. That means the bond. And that bond is basically is your nutrient, the fingerprinting we're looking at. So that means as we go through some of the nutrients, those are limited in terms of how much, what is their bond energy is there, and the light source we are providing may not have a direct implication or direct connection. Due to those differences, some of those properties are not easy to measure directly. So again, one way I can say, oh, I have a spectral data. I can actually calibrate the spectra with any number using a mathematical algorithm and say, oh, this is the prediction of this. It's possible, but truly think about the physical meaning of it. You really need to go back and try to see the fundamentally how the spectroscopy is working and what is the capacity of the wavelength or waveband you are providing into soil and what is their connection to the soil properties. If you go beyond there, you can only develop that secondary relationship or tertiary relationship to talk about. If you think about calcium, often very correlated with the organic matter, and that could be correlated to your spectral band because we know the fingerprint within the range of spectral band we are approaching. But if you think about phosphorus, it's always been a notorious in this case. And I know even I work with farmers, everybody will say nitrogen, phosphorus, potassium, calcium, sulfur. Can you give me those data so that I don't have to wait for it? I can do a decision making. But many of those properties are not directly related to the waveband we are looking at. So in that case, we try to develop the secondary or tertiary relationship. But when we are developing that secondary and tertiary relationship, we have certain limitation. So it's not a direct relationship. I have seen papers where you're combining with something else. There's no connection. This will be one message to everybody when we're using the spectroscopy is that think about the physical meaning to it. Think about the energy you are shooting into the soil and how that energy is associated to the different fingerprinted materials or different constituent of the soil. If it is not directly a primary relationship you find, then try to develop a secondary or a tertiary relationship. But be cautious about what it can say. So that means from a farmer's perspective, of course, I want that data set, but some of those data set, we have that fundamental limitation. So again, you can train a person to play a basketball, and that kid, you can go there and ask them to play volleyball. For the first time, they won't be, but they are a very good sports person. So what you have to do, you have to train them to be a couple days to actually suit to that condition so that creating the secondary or tertiary relationship, you can actually, that person could play well. So that's the same way when we take that spectrometer data and try to get that relationship. I think we need to think about what is the direct relationship, what is the secondary relationship we can build, or what is the tertiary relationship we build. But we need to, every time we need to go back, what is the fundamental of that spectroscopy? What energy source we are using? What energy source could excite certain amount of bonds, so certain energy in the soil as well, and that is associated to that property. So I know this is not a solution. Can you do it? I have to give a long answer because there are some challenges and what we can do and what we cannot do with that.
Yes, this is something I also come to the next question is because I think there is a little bit misconception in a society thinks spectroscopy can solve all the problem in once. I would say none of the technology can solve all at once, and that's why there's another question is asked that can you talk a little bit experience with the detection of the metal and a non-organic material from using NIR?
Again, going back to my answer, like the property you are looking at, what is that energy source? What is the fundamental chemical constituent actually contributing there? And are you providing the range you are using? If you're using a 350 to 2500 nanometer, like a full range of NIR, visible and NIR band, do you have enough energy source within that band of your choice to excite the material in your soil? Can you see the similar? If it is a high difference, then really not marrying that one. It's not matching up that fingerprint. So whether it's a non-metal or metal or some non-organic carbon material, so you have to be thinking about what are those energy source? is my energy source good enough to actually fight for that or try to develop a relationship for that? If it is not, then what's the secondary relationship? Is there a secondary relationship that non-metal, that non-organic carbon material, non-carbon material is associated to a maybe carbon material, maybe moisture, maybe some textural impact, mineralogical impacts out there, and that could be predicted. So you are trying to take that secondary route, tertiary route to develop. But some of the cases, like, yeah, it doesn't work. Like in that case, like I cannot solve everything because this energy band is very narrow. You can think about even some of the spectrometer are only using like 400 to 900 or maybe 900 to 1700. So we have that limitation as well.
Yeah, that's the assumption from the raising awareness level. We also need to do something to let the society knows every technology has their advantage and also disadvantage, also the limitation. It's not something superpower technology.
Yes, it's not
Yeah.
possible. Yeah.
Just a quick question here, actually, before we go into the end. One of the audience, Benjamin, is asking if you have a GitHub for R code. I mean, before you answer, is that actually we are in FAO, we are currently developing a publication to trying to release some R code for the chemometrics, and we are working with Alexander Wardle recently, and we expect to release this publication by end of this year, and we'll put in the GitHub for all the R code. So I don't know you.
Same thing, I would say we don't have the particular all this R code into GitHub yet, but some of the soil mapping and some of the soil codes are already, we have been doing last 1 year. We have uploaded many codes out there. We are creating whether under the Biswas Soil Lab GitHub directory or even my students, different students have their GitHub directory as well when they are working on their individual research as well. So at this point, not specific to the transformation and all those things in the GitHub available. But some of the other codes are available, and we're hoping to continue to contribute there. So that means continue to develop more and more code available for others to use.
Yeah, thanks. I think the last I would like to also have it's also a couple of a little bit tricky question for you to answer, and it's good to use this opportunity to clarify some misconception to our the colleagues from society. Why is the I think the first question is basically asking if one day we can use spectroscopy to replace the red chemistry.
In an idealized world, I want that, but can you do it? I think probably not right now. Can you do it in 10 years? I don't know. So we can all work together. But I think in a most idealized world, probably we can reduce that impact. We can reduce that dependency on that so that we still can, like, for example, technology testing, some of those things you'll continue to do that. So that means every time you have a new spectrometer coming in, new equipment, new technology, how do you test it and other things? We still have to go through the world chemistry because that's what we believe to be the soil property we're looking at. And so again, this is an open-ended answer, like, and I cannot be definite here. I want that. Yes, I want to do that, but can we do it? Probably not now. In future, maybe, but maybe not. But I feel like still there will be a leveraging approach in there so that we can reduce the dependency on the lab-based chemical analysis and try to leverage more and more the spectroscopy-based analysis. This is my way of seeing future.
Yeah, I think I definitely agree with you. At least in this stage, we should only consider spectroscopy as just one of the alternatives for the soil analysis. And we should not, I would say in the coming some years, I should not consider to completely replace the wet chemistry in this sense. And I forgot one of the interesting question. I don't know if you have this experience or not. One of the colleague asked if you have any experience to use spectroscopy to detect the soil salinity.
Not exactly, but a couple of the other studies we try to do that, combining with other techniques as well, not solely depending on that. Particularly, the main reason is that we tried some of the EC measurements, which is not exactly the salinity, but it is a representation of the salt content. We try to do that some cases with the success, but some cases not. So now if we really take it out to the field level, I think for the salinity detection, rather than the spectroscopic range we're looking at, some of the other electromagnetic range could be more suitable to detect those salinity in the field condition. So like, again, based on the energy source we are providing in the soil in the form of that vis-NIR, so I think there could be subsidiary other technology would be more suitable for salinity, and which you have seen in the community, like other EM-based techniques, MI and others.
Okay, thanks. I think it's been 1/2 an hour this webinar, and we can, yeah, time goes fast, and I think we can go to the last question for the kind of a closing our webinar, and this question is actually it's asking, is the precision good enough to detect different different soil properties with the soil spectroscopy? And in the same time, I saw another question posted by the colleague asking, how about the wet chemistry laboratory wet chemistry era? Actually, this is the point, because we commonly consider that is the best reference, but actually, when you look into it, it's actually unbelievable. So it's good enough or not, I think it's depending on different perspective. So I will give this
Absolutely.
floor to you.
I think there's a different way we can say that, but often what I say that, do you want to be 50% accurate or want to be 100% wrong, like every time, and 100% right about 100% wrong? I like to be 100% wrong, 100% right about 100% wrong, rather than 50% right about 50% wrong. So what does it mean is that if my spectrometer is stable enough, try to repeat that data collection again and again and again. So the consistency, robustness of your spectrometer and the energy source and other things you are using, so that it's consistently generating the same spectra from the same soil in the same condition. So that could help you detect the change, detect that minor variation. But just like the wet chemistry, wet lab, in my lab, the way I can look at it, another lab, my colleagues' lab look at it in a different way, there is always those variations out there. And we know the lab to lab variation is quite a big. I have done that, and I'm pretty sure all of the researchers have done in their life, sending the same sample to multiple lab or multiple time, or multiple students are working on those and see the differences. This is like curiosity. We all have the research, and I'm sure if you're running a soil science lab, you have done this kind of a social experiment. So the same way, those variations, again, the source, the tools that you are using, different energy source and like power and all those things. If you can be consistent on that, I think that is good enough to actually detect those changes, small scale changes. But just like the way we have seen, again, even if we can detect those changes, we are trying to predict it back against the lab data, which already has uncertainty in it. So now how we want to see that? We want to generate an uncertainty from an uncertain data. You have to keep it in mind that one. Now, if you try to talk about, oh, can we go for a 1 ppm variation in this case? The first question I would ask, like that 1 ppm variability is an absolute variability, or it could be variable. It could be uncertain based on the location or based on the person that generated the data. Then I will come back to, is my sensors, is my equipment is good enough to be robust enough to get the data consistently, or there is a variation between the sample collection. Even it could be wrong data, but the wrong is 100% right time. 100% time it gives the wrong data. So then you can get the robustness, you can get the consistency. But 50% time giving you the right spectra, 50% time give a wrong spectra, that value on anything compared to if you 100% time, get the wrong spectra, but it's a consistent spectra. So it's good to be 100% right about 100% wrong.
Yes, I agree with you. And also from another perspective is when you ask is accurate enough or is good enough, it's also depending on your application. And I always talking to the tell colleague, I said, for example, if we want to, we use this technology for the fertilizer recommendation. So basically, we need to estimate some soil nutrients related properties, and afterwards, you need to give some you need to use these predictions for some formulas to develop the fertilizer recommendation. And that time, you cannot tell farmer your land need 3.4 kilo of the nitrogen or 7.5 point. Is either 7 or 8 kilo. So it's depending on the what you expect.
And even you often like, this is what some of the other work we have been doing in the digital agriculture in my major research, like we have always seen what is the spatial resolution I look at. I probably look at a still my corn is a 30-foot planter. So basically a 10-meter planter. So any data I generate less than 10 meter might not be very helpful because I want to control my seeder. I want to 8-row or 12-row seeder. I can only control that. So that means at a time how much I can control. And then what is the information I can generate? So again, generation of the data and a true implication and actual use out in the field. Even 7.5 or 8 or 7, sometimes people say, oh, I need a 10 pound or I need a 5 pound or 15 pound,
Yeah,
even that sort of
exactly.
course. So some minor variation here may not at the end really helpful for the application purpose. Yeah, research, absolutely necessary. We want to develop technology. We want to confirm our findings. But in the application case, we have to generalize some of those things.
Yeah, exactly. Yeah. Thank you very much. It was a very
I
interesting
want to
discussion.
mention, like, I know a couple of the question I'm looking at. I'm sorry that our
No, yes,
presentation is in
please.
English, and I know some of the linguistic barrier out there, but I think this presentation is recorded and will be available. I see at least two or three comment with the linguistic barrier and getting the true sense and what FAO is doing, but we are trying to work out as much as we can to reach out. And GLOSOLAN Spec, I think, has done some of the other workshop in other languages as well to help increase that visibility.
Yeah, this is something in the end I would like to answer a couple of
Okay.
general questions.
Yes.
One is that, first of all, I think many colleagues asked if we will release the video recording or not. Yes, short after, I think it's just in just a couple of days, we will upload the video recording and also the slides in a PDF format in our website where you did the registration. So please follow our website and regularly check because we will have coming webinar as well in May. We will have the using have Asa to introduce her experience using spectroscopy for detecting contaminants. And also in May, we will have our first Spanish webinar, and I saw some colleagues, French-speaking countries, asked if we can organize some French-speaking webinars. Yes, we will try to work on that and try to provide this knowledge share platform in multi-different languages and to facilitate the colleagues from a different part of the world. Uh, so our webinar is coming to the end, 1 hour and 40 minutes. I think I would say it's very successful, and I would like to thanks to the Asmin and your colleagues. I believe they are even more stressful than you because in the end we ended up like 60 questions in the end. Yes, and
No, thank you very much. Yeah, no, thank you to FAO and GLOSOLAN Spec community. I really appreciate you all showing up, and I would be happy some of the information and other things already provided. Any question, reach out to FAO, the community, or to me directly. We can always answer more.
so if any colleague from any part of the world, any lab, if you are interested to get in contact with Asmin, please let me know. Of course, they already shared the contact information in the chat, just in case if other watching the recording videos and then they found that your work is interesting. So please feel free to reach me and I will help you to get in touch with him. And in the same time, thanks all of you in the panelists that try to help with questions. And we did a great job today together. And so thank you very much.
Thank you, everybody.
Yeah. Okay.
Bye for
Bye.
now.
See you next time.
See you next time.
Yeah.